Thank you. Yeah, so actually I don't really know what to expect myself. This is a bit of an experiment, so that's why I wrote, hey, would you be interested in this talk? Just something I want to try out, so maybe you can, afterwards, you can come up to me and just tell me, okay, that was total crap, like, it makes no sense to talk about this. So, yeah, so, because I've already said, so I have a physics background, now I work for T&G, and I like Node.js, JavaScript, and doing software development, and I have this physics background, so I was thinking, well, how about like trying to find something to combine the two things, and this is why I sort of came up with this idea with this talk. Change the title a little bit from what is in the announcement, so I call it Quantum Non-Locality for Node Hackers. So there's no more physics in there in the title, and actually the talk will not be about physics, so there won't be like barely any physics in it. So hopefully you'll see what I mean later. Okay, sorry, that's wrong. This physics. Yeah, it's really cool. There's like a space background, which means it's really, really cool. So quantum physics, of course. Why am I giving this talk? Like, why am I? Do I want you to get excited about this? Maybe you've heard about it. Like, there's all kinds of fancy buzzwords about this. So Christoph already mentioned quantum computing. There's like this concept of spooky actions at a distance that Albert Einstein was sort of skeptical about. Something called entanglement, which you might have heard about. Yeah, something fun. Quantum computers was already mentioned. So there's all this stuff. And there's one thing I would like to focus on in this talk, which is, I think, yeah, quite a remarkable thing. This concept of local realism. So quantum physics says goodbye to local realism. So what is local realism? Yeah, I'm just going to quickly explain to you what I mean by that. So there's like these two words, locality and realism. So locality in physics means that something that happens at one position cannot have an immediate effect on something at a different position. So you need some sort of finite speed of information between two different events in the universe, this concept of locality. And realism is also something that like many people would just call common sense. Stuff in the world exists independently of observers, so it's sort of this idea of the moon. Is the moon really there if no one looks at it? And if you're a realist, you say, yes, of course, like it's a real thing. It doesn't matter if I look at it or not. So it turns out that in quantum physics, you cannot have both at the same time, which I find quite remarkable. You have to either say goodbye to locality or realism or both. And why is that? So there's a concept of Bell inequalities, which John Bell came up with in the 60s. So he wrote down some very precise equations that, well, they're not equations, but inequalities that, if violated in an experiment, would prove that the physics cannot be locally realistic, so it cannot fulfill locality and realism at the same time. One of these Bell inequalities is called the CHSH inequality. It's really quite simple, actually. And the nice thing about this particular one is, or actually about all of them, you can formulate them as games. So this one can be written, like you can make a game out of it. And this is what I'm going to show to you. So I'm going to develop a game in Node.js to explain to you this concept of the CHSH inequality and of local realism. So why do I think this is fun? I think it's fun, and it's a nice thing to talk about at a Node.js meetup, because in my opinion, it's like really one of the most profound discoveries of last century. So there's, I mean, you've heard of like quantum mechanics itself. There's like general relativity and all kinds of things that have been discovered and that people came up with. And there's also this thing. And you don't need to know anything about physics, in my opinion. You just need to know Node.js to grasp this. So was there a question? Or, no?
Is it easier?
The teaser, yes.
No, that's actually easier.
Is that easier? Yeah. Well, this you can decide for yourself. So you're obviously all Node.js developers. So maybe for you, yeah, trying to sort of get through to you by talking about this. Okay, so this is the introduction. Yeah. So this is what I'm going to talk about. I just talked about the introduction. Yeah, I already mentioned the CHSH game. I'm first going to explain to you what it is. Then I'm going to show you a very simple implementation in Node.js. I'm going to talk about how do you win at this game? How do you get better at it? What is the best strategy? I'm going to quickly talk about what a quantum bit is. And all in between, I'm going to show you like how you can simulate these ideas with this Node.js game that I made. And in the end, I'm going to close with some general remarks about like what we learned about quantum non-locality. So let's start with the CHSH game itself. Let me introduce the players. So CHSH game is a game for 2 players. One of them is called Bob. The other one is called Alice. So you might be familiar with Bob and Alice because you're computer scientists. And the CHSH game is a game you play cooperatively. So you either both win or you both lose. And there is a referee in the game. So these are the protagonists. There's Bob and Alice, and there's the referee. You have the 3 of them.
Is that Schrödinger's cat?
Very good question. Maybe it's Schrödinger's cat, yeah. I thought about this. This would maybe add a twist to the whole story. But it doesn't matter right now. It's just a random referee cat. Yeah. Both it is and isn't at the same time. So the rules of the game, Bob and Alice play the CHSH game with each other cooperatively, and they're separated far apart, and the referee is in the middle. And it's very, very simple. The referee asks Alice in each round of the game, so it's sort of a round-based game, the referee asks Alice and Bob a question. And the question is just 1 bit, so it's just 0 or 1. Of course, I mean, it's not really a question, but it just gives you a bit. That's what I call a question. And in each round, Alice and Bob each give an answer, which is also just 1 bit. It's very simple. And because they're far apart, they do not know about the question that the other player has been asked, or which answer the other player has given or will give. So we have this situation. We have the referee in the middle, and it sends out a question Y to Bob, and at the same time a question X to Alice. And they answer with an answer B from Bob and an answer A from Alice. But Alice and Bob do not know what the other player has done. So we have this situation. And now this is very simple. This is the only math you need to know for quantum non-locality. So this is just the rule of the game. So Alice and Bob win if the product of x and y equals a, x, or b. So a and b, so remember they were the answers of the players, and x and y are the questions. So x or you know because you're programs. And just to explain, so what does it mean? So Alice and Bob always need to pick correlated answers. So they always win if they give the same answer, except for the case that x times y equals 1. So which means that if the question given to Alice and Bob are both 1, then Alice and Bob win if they pick anti-correlated answers, so 0, 1 or 1, 0. In all other cases, x times y will equal 0. So Alice and Bob have to pick the same answer. They have to pick 0, 0 or 1, 1. And there's no cheating. So that just means what I said before. So Alice and Bob cannot talk to each other once the game is started. So they have to sort of do something now. Well, they can, before starting the game and playing several rounds, they can come together and agree on a strategy. They can say, okay, let's just do this thing where whenever I get whenever I get 1, I will answer 0, and you do something else. Let's try to find a way to get good at this game. Okay, so I implemented this game as this is the wrong key. Node.js application, but I just use very simple tools. I could have done it in loopback. Maybe I should, someone should help me write this in loopback. But what I did was I'm just opening network socket, TCP socket, like a server, and 2 clients that can connect to the server and play the game with the referee. Just going to show you how it goes. I have some source code. So I just use this create server from the net module. So this is just like Node, everything that Node already comes with. And I create a server on a certain port. And I allow 2 participants to connect to the server. So I first have, the first player will be Alice. So if Alice connects, then I create this sort of player socket object. The next player will be Bob. And I also create a player socket object with just a different name. And then I start this CHSH game. So by the way, I use TypeScript. I think it's a nice way to program in Node.js. So let's just look at what happens here. So these player socket objects, they're just, I have a generic interface called player, which just has a message function that sends a message to the player. For example, you've just been asked a question. Then it has a register input handler, which allows me to register sort of a callback function for if I want to provide an input. And it has sort of this generic get player name. And then I have a player socket, which is the socket-based implementation, so the network socket. In this case, I just, for the message function, I just say socket write, so it just writes something on the TCP connection to the player, and register input handler just passes on this handler, this callback function onto the to the callback. Like whenever the socket receives some data from the player, then it just calls this callback. And let's go back a step, see what the game does. So I start a game with Alice and Bob. So this is, of course, it's a stateful game, so I always have to track like whose turn is it, like has Alice already answered, has Bob already answered, because they always have to provide answers. So I have this game state class, which sort of takes care of that. So it has it just basically implements this game logic. So it has like some methods like player input, waiting for player. So I have some way of tracking whose turn it is, who has to do something next, and then I have like get score, which calculates a score. And it just basically has this function winning, which basically just implements this this one rule of the game that I just showed you before. So they win if the product of the questions they've been asked is equal to the XOR of the answers. Maybe I'll just show you how it works. So I just start the server. Let me just connect by hand. So I started this TCP server, and I just connected to localhost port 8000 via telnet, and now it tells me you're Alice waiting for Bob to join. So I connect a different player. Okay, now my other player is Bob. And now the game starts, so they both being asked a question. So the referee question asked to Bob is 1. I can give an answer now here. Maybe I'll say 1. And maybe Alice answers 0. And now it just prints out a little summary. So the question to Alice was 1, the question to Bob was 1, Alice answered 0, Bob answered 1. And yes, I won because the winning condition was fulfilled. And then it gives me a little percentage. So how many games out of the games that I played did I win? Okay, so that's pretty simple. Let's talk about strategies to win the game. So, I mean, it's actually pretty simple. So, of course, you can think of just some rules to follow if you're playing this game. And this is what I call a deterministic strategy. So it's a strategy where Alice and Bob just follow a set of rules. So they always sort of deterministically come up with a specific answer given some specific question. There should be some, oh yeah. So Alice and Bob, now they come together, they decide on a strategy to play this game. So one thing would be to just always agree, like if you're thinking about deterministic strategies, just always agree to pick the same answer. I already showed you that there's this one case where you wouldn't win, which is when both of the questions are 1. But you win in 3 out of 4 cases, so the winning probability in this case is 75%. Since there's only one case where different answers would win. And I mean, it's pretty simple to see. You can basically just enumerate all the different strategies. You can come up with the different deterministic strategies. Just write down a table, like what happens, what are the possible strategies that I can do, and it's pretty quickly you come up with the result that this is actually the best you can do deterministically. I'm just quickly going to show you that as well. So I implemented a client for my game as well. And I can pass the client a strategy. So I implemented this interface game strategy, which basically just tells you what will happen if I'm given a specific question and it returns an answer, or the promise of an answer, because it might be some async stuff. And in this deterministic strategy, what happens is whenever I'm given a question, I just ignore the question and I return a promise that immediately resolves and just answers with 0. So in this case, Alice and Bob just always answer 0, which is this best possible deterministic strategy that I told you about. Because they always agree to pick the same answer, and it might be just 0. Doesn't matter which one it is. Yeah, and now this client just like it connects to the socket, and then whenever it receives a referee question, it comes up with an answer. It writes it to this TCP socket, and it increases the counter. So let me show you that. Actually, because I changed the comment here, I should recompile or let the TypeScript compiler run. And let's kill this server, and let's run a client which uses this deterministic strategy. Now it still receives the messages from the server, so it receives this URL is waiting for Bob to join. Bob, I can of course play Bob manually now, but I'm also just going to use a client for Bob, the automatic client. And now that we'll just start playing the game for a while. Yeah, and you can see that this percentage of the games that I won, it sort of converges to 75%, which is this 3 out of 4 cases where this strategy makes sense. Yeah, and then I just have like a cutoff, like at some point I just stop playing the game. So it's not, I mean, I was actually curious about why it doesn't like just completely go to 75, but because it doesn't seem to help to play the game longer. So my guess is that the random number generation in Node.js is just not really good, but maybe someone else has a different.
It's not really random.
Yeah, it's not really random.
Random.
Yeah, I know that, but I sort of would have expected better. I was a bit disappointed with this, but it's fine. Yeah. Okay, let's mix things up a bit. So let's do something more. We already have this sort of this question that is being sent to the players in each round is a pair of classical bits. So it's just a 0 or 1. Let's send out an additional pair of classical bits with each question to the players. So now there's actually 2 different bits sent out. Let's just like ignore this additional pair of classical bits first and ask whether this is against the rules of the original game. And no, it isn't, because these additional bits, they're not correlated to sort of the questions that are being asked. So Alice and Bob have no way of inferring some information from them. So it's not against the rules of the game. There's no possible way to communicate while being in the middle of the round. So we have this situation. So we still have the referee, still have these questions X and Y being asked. We have answers A and B being given, but in additional, on top of the referee, there's this light source and sends out a photon, and a photon in physics can have a polarization, and it's just 1 bit. So it can be like up or down, for example. So there's an additional 0 or 1. Yeah, let's set things up such that this additional pair of classical bits is always anti-correlated. So whenever Alice receives a 0, then Bob receives a 1 and vice versa. But keep in mind, they're not correlated to the X and Y, so they have nothing to do with them. So Alice might now just like make her answer A depend on whether she sees a 0 or 1 in the additional classical bit. But it's not really going to help them. But this is a situation called shared randomness. So Alice and Bob, they can agree on a deterministic strategy, but they can also share some additional randomness between them. So for example, they can have this additional pair of photons that are anti-correlated, and they can use the questions, for example. I mean, they might have a photon measuring device for measuring this additional classical photon, and maybe this measuring device has some settings, and they can use the questions that they receive as settings for the measuring device, and then they measure this additional classical bit, and they get out a 0 or 1, and they can use that as the answer. But it's not against the rules of the game, because this 0 or 1, as I said, has no correlation to the questions being asked. Okay, so I also implemented that. So what I now have is I have 2 servers in the middle. In the middle, I have this game server, which you already saw. I have another server, which provides these anti-correlated pairs of additional classical bits. Then I have the client, which now connects over 2 sockets to the 2 servers. Yes. And I will just quickly show you. Okay, so yeah, I think it's this experiment photons. Yeah, so I create an additional server here, which just says sending out photons. And again, I allow 2 people to connect to this photon experiment. And the experiment is encapsulated in a different class called experiment, which has a pair of classical photons. The quantum photons will come later. Yeah, and they now send out these photons. And what Alice and Bob do is, so there's this class, classical photons. So classical photons means, as I said, Alice and Bob, they can measure the configuration of these photons that they get, and they can have different settings of their measuring devices. I have the setting 1 and setting 2, but they're just ignored. And just with a 50% probability, Bob will receive a 0 and Alice a 1, or in the other case, Bob will receive a 1 and Alice will receive a 0. Yes, and then what they actually will output is they will measure a. Okay, I just showed that. Yeah, that's just the interface for the shared photons. Yeah. So they will take that and measure their photon and use that as their answers. So now what I have to do is also in the client I have to say they're going to use this photon measuring strategy instead of the deterministic strategy now. Let's just run this again. Let's run the game server again and also run the photon experiment, which now listens on a different socket. And let's run a client and the other client. And you see that now by using the strategy where they sort of make a measurement of the additional bit and then they output the result of that. Yeah, it's pretty much just random. Their strategy is like really, really bad. Just win in like 25% of the cases. Okay, we can just let this run. Don't have to show this. Okay. So with shared randomness like that, you don't get any improvement. You can also do this more formally. You can write down any sort of shared randomness strategy, and you can see that they will just get worse than the best deterministic strategy. Okay, let's see how the situation changes for quantum bits. So what is a quantum bit? I was already talking about photons for a reason, because a photon is, you can see it as a quantum bit, very simplified version of a photon. So I told you it has a property called polarization, which when measured just gives you a bit. So you can measure up or down. But a photon cannot just be in a specific polarized state, but can be in what is called a superposition of polarizations. This is also what, for example, a quantum computer would use. You can have a bit or a qubit, which can be this sort of, it's not just 0 or 1, but you can have sort of this expression where C1 and C2 are coefficients, which give you sort of an idea of the probability that when measured, you find this photon in the state 1 or state 0. And these are also complex numbers, so you can have like a phase factor in between them. Let's now modify our setup in such a way that these additional bits that Alice and Bob receive, they're now quantum bits. So they receive a pair of quantum photons in such a way that, as before, whenever Alice gets a 0, Bob will get a 1. So that's sort of these two terms here, factors. And in the other possibility, Alice receives a 1 and Bob receives a 0. But now this is not like, it's not just classical randomness or something, but this is really two photons that are said to be in this quantum state. So this is how you could set up an experiment to provide these photons for you. And now what Alice and Bob do is they measure the polarization of the photon as before. But now this polarization you can measure along a different angle. You can choose a setting of your measurement device that I already mentioned. And as before, you can make this setting depend on the referee question that you've been asked. And the result will be the answer to give. So this is an additional illustration. So you have this photon source, which gives Alice and Bob each a photon. And this polarization you can see sort of as you put in a filter which sort of filters out some photons along a different angle that are polarized in a specific way. And there's two possible settings, so they're called here XA and ZA, or XB and ZB. And you can make a measurement of your photon in that way. But you always get a result of 0 or 1. Yeah, you can calculate what the probability distribution is in a calculation quantum mechanically. And that's what I did. So I implemented this quantum photon strategy in Node.js. So now I'm still going to use the photon measuring strategy, but instead of, yeah, what am I actually going to do? I'm just a bit lost here. Shared photons. Instead of using these classical photons, which you would just always get this 50% 0, 1 or 50% 1, 0, we now use the quantum photons, and you have to do a quantum mechanical calculation that gives you the probability that, for example, Alice makes a certain setting of a measurement device and gets a certain output, and Bob makes a certain setting of the measurement device and gets a certain output. So I'm not now going to use the quantum photons. I'm going to rebuild my project. Going to restart. Restart the game and restart the experiment. And run the client. So what do you think will happen? Will I be able to do better than before in the game? It's sort of a stupid question to ask, isn't it?
With a probability of 0.5, it will be better.
Ah, okay, interesting. Yeah, maybe, I mean, this is all like, it's not really live coding like Andreas did, but still things might happen, so maybe it's, yeah, this is, yeah, okay. Yeah, I was actually a bit scared that I will just get 75%, but it seems to converge to sort of like 85%, so I'm able to beat this 75% bound. So, I mean, now you have to, like, actually, you should be really, really surprised to be like, whoa, because this should be, yeah. So why can we beat the CHSH game? I mean, we have the situation where we just, like, we get these referee questions, and we have no idea of, like, knowing which question the other player got, and we got these additional quantum photons, which are not correlated to the referee questions. Until Alice makes a measurement. So she makes like a setting of a measurement device depending on the question that she's been asked. But if you sort of see something like this, like you see, you can sort of get better at sort of this collaborative game. So why can you get better than like the best thing that you can possibly imagine in a classical world? So like one option would be you have some sort of spooky action at a distance, right? Because you sort of you sort of, Alice makes a measurement at her device, and like immediately it sort of has an effect on Bob, which then influences like his outcome of the experiment, and then sort of some information of the question that Alice has been asked leaks over to Bob. That would be sort of a spooky action at a distance. Or the other option would be that the outcome of the measurements that Alice and Bob made, they are not predetermined, so that so only when Bob sort of decides to make a certain setting of his measurement and Alice makes sort of a certain setting of her measurement, then sort of the photons sort of decide in which state they're going to be in. Because that would also be like, make it possible to sort of have a correlation between Alice and Bob, which is stronger than just by if they can't communicate. And this is exactly what, like you have these two options, you have non-locality or non-reality. So like you have to have one of these two explanations. Yeah, and so then I want, like this is a test question now. So like why can I do this on my computer? Like, do I have like some sort of quantum experiment in my laptop that allows me to beat the CHSH game? Like, do I have a network socket, some sort of quantum channel, and I can send quantum photons?
You didn't show us the code of the quantum photon.
Yeah, I didn't show you the code, so I'll show you the code. Yeah, so there's some like probability of like given a setting, what is the probability of a certain outcome? And yeah, then I sort of sample from this probability distribution. So I have two settings, and then depending on the two settings, I say, okay, this is now my outcome, and in the end we'll fulfill some probability distribution. So do you think that's fair? Do you think I'm allowed to do that in the CHSH game? Or
Yeah, that's the strategy that Alice and Bob designed on.
Say again the last, the strategy that...
That's the strategy that Alice and Bob decide on, how they work on the problem. And
Yeah.
of course it only works because there is the photon
Yeah.
sent out.
Yeah, yeah.
But it doesn't interfere with, or it doesn't correlate with the question, so
Yeah, yeah.
why not?
Well, I mean, I'm actually, yeah, okay. Maybe I'll give you a little hint. So I'm actually cheating here, like when I do this simulation, because I just have this like, I have this one server in the middle which gives me the result of my photon experiments, and it waits for Alice's input. Like it says, okay, Alice chose this measurement setting and Bob chose this measurement setting, and then it gives me some results. So there is some leakage of information into the server. So because I just have this one, I have everything run on one machine, so Alice and Bob, they're not separated, but like sort of their settings, they come to the middle, and then they, no problem, and then they, I decide on the outcome of the experiment that I'm going to give to Alice and Bob. So this is why I can like easily beat the CHSH game. I mean, you can just trivially beat it by just saying, just writing like a server in the middle that accepts Alice's question and Bob's question, and then tells Alice and Bob what to do. Then you get 100% easily. So this is a little bit like that. But you have to keep in mind that if you do this in an experiment, you don't have anything like this. You don't have like a server in the middle, but you really like send out quantum photons, and the measurements they're like done in like remote locations. Yes.
Yeah, as you say, like you just kind of cheating. In the real world, it would be more like if you were really playing with quantum photons, it would be like in the moment that I measure something in this place, it will become like real in the other place. So at the end, there's no communication. There's some kind of communication because the act of measuring is actually revealing the position of the other.
Yes, yes. So, I mean, you have to, in the end, if you do the experiment, you have to conclude that the act of measurement sort of does have some effect on Bob. Whether it's through sort of non-locality or non-reality. I mean, you can't really just decide which one is true because they're sort of undecidable. You can write down a theory like that's like very real but like non-local, or a theory which is local but doesn't have this reality aspect. And you cannot decide which one is true because they're equivalent in the end. But as you said, that's exactly right. So if you have these two remote locations and you do the measurements, then you have to conclude that by making this measurement, I sort of leaked over my information to Bob somehow. Yeah. But on the computer, I can't really do it, of course, because the computer, I mean, I can just, as I said, I can just write like a strategy where Alice and Bob, they just give their answers to a server, and the server then just provides, or they give the questions they've been asked to a server. The server just provides the answer that would make them win the game. So then we'll just get 100%. Yeah, so I didn't implement a quantum computer Node.js. So, yes. So just some final remarks on quantum non-locality. So the nice thing about this, in my opinion, is like the rules of the CHSH game assume nothing about physical laws. To be able to like grasp this CHSH game and like to decide if you're beating the 75% bound or not, you don't have to know anything about physics. This is called device independence. So what does it really mean? So imagine you wake up in a foreign universe. And obviously, like when that happens, you decide to play the CHSH game. Yeah. And let's say you beat the 75% bound. So you just like, you found a friend in the foreign universe, and let's say play the CHSH game like 10 kilometers apart. And then we just managed to somehow beat the 75% bound. And this means you're now sure that the laws in this universe do not obey local realism. There must have been some leakage of information between us, like without knowing anything about physics. So you haven't made any assumption, or you don't have to know. You just have to know that you're following the rules, so that you're not actually sending some information directly to your partner, but you just play like separate. You have your own devices, and you sort of, in an experiment, for example, you have to make sure that you time your responses like correctly, that you don't have any chance of even communicating between receiving your question and giving the answer. So does that mean that we can do faster than light communication? Many people have thought about this when this thing came up with Bell inequalities, and the answer is unfortunately no. Because in this game, like you saw that you can sort of, I mean, Alice and Bob, they play the game, then they come back together, they compare their results, and then they see, oh wow, we somehow have some good correlation, so maybe we just send some information. But then if you really like think about it, you cannot really do anything before coming together. So while they're far apart and they're playing the game, they do not know anything about whether they're winning or not. It has to be the referee in the middle to decide. So they have to like go back to the referee and ask like, okay, how well did we do? And unfortunately, there's no way around it. You cannot really communicate something instantaneously with this. Okay, then there are all kinds of loopholes. So when people started doing actual experiments and they saw, yeah, we can actually do this, then of course you can come up with all kinds of conspiracy theories. So you do this photon experiment and then you say, yes, but the Alice and Bob, they were not really that far apart and there was like some time between the measurements, so maybe there is some sort of hidden communication between them, or there's also another loophole. If you cannot really detect your photons very well, and you might be able to just like select the photons that sort of play in your favor and like discard the other ones, but then you can also like beat this bound without actually proving this non-locality or disproving local realism. But like as of now, like all kinds of experiments have like been done, and these loopholes have all been closed. So there was a recent one, well, not so recent, but 2015, which like by many regarded as, okay, this is like the final thing that like closed all the loopholes. They did some of these. They played the CHSH game with some quantum bits. They didn't use photons, but electron spins separated like 1.3 kilometers, and they found they could win the CHSH game better than in 75% of the cases, and they sort of set up things in such a clever way and used like very, very good detectors that actually they were able to close all the loopholes. So in the end, you have to accept that you cannot have a locally realistic theory of nature. Yeah, that's it. So if you have any more questions, then